Okay, so my goal today is to try and convince you that yes, you, watching this video, could have invented the notion of semi-direct products. I'm kind of stealing the title a little bit. There's a document out there called You Could Have Invented Spectral Sequences. There's a great video, which I've linked to before, by a now defunct channel, Bourback called You Could Have Invented Homology. So this is named as such in a similar vein. So semi-direct products of groups. This is some way of combining groups. How do we approach this problem? Well, what does it mean for one group to be built out of another, right? So the idea is I have two groups, say G and H. I want to understand all groups, right? So I'd like to be able to take a group and pull it apart into its constituent pieces in order to better understand it. And given two groups, I would like to recombine or simply combine two groups to get a new larger group, right? And the idea is, well, maybe, sort of taking a reductive approach to thinking about groups. The hope is that, well, if we can, decompose a group into its constituent pieces and then reassemble it, perhaps we can learn everything, we would like to know about the group by breaking it down into this simpler problem. So as you know, one way to, presumably you're watching this video if you already know that one way to combine two groups is to form the product of two groups, right? So if we're thinking of these, this is just the set of all pairs of elements in G and H, where the group operation GH plus, KJ, whatever, is just done component-wise, right? So that is definitely one way to take two groups, put them together, and get a new, larger group, right? But is this the only way? So how are all groups built? So if I have some sort of group G, I may wish to better understand its structure. How might I better understand the structure of G? And maybe it's a very complicated group, right? Well, one possible thing we could do is we could look at a subgroup of G, right? So if H was a subgroup and maybe that subgroup is easier to understand, I could go and look at the elements of of the elements of H, do some sort of math with that, right? Better understand the structure of H, and that at least gives me some insight into the structure of G. But if H is really small compared to G, then I'm missing a lot of elements, right? So what do I do with the rest of those elements that are lying outside of the group G, right? H could just be this very small portion of it. How do I understand those elements? Well, there's another way that we can investigate a group. So let me put it to you this way. What is our one way? We really have one way about talking about the relationship between one group and another, right? So I would like to somehow say I have two groups N and Q, and you'll see pretty soon why I'm choosing those letters. And I would like to somehow, build a larger group G out of N and Q, whatever that means. This is very vague and imprecise at the moment. So I want to build some bigger group out of N and Q. And well, how can I relate these groups to each other? Well, that's what a group homomorphism is, right? That's exactly the right thing to use to have two groups communicate with each other, right? So we can have homomorphisms going into groups, and we can have homomorphisms going out of groups, right? So I might ask for some homomorphism that it goes into a group, and I might ask for some homomorphism that it goes out. So, okay, maybe talking about how G is built from N and Q should have something to do with homomorphisms coming in and out of G. Okay, hopefully that seems reasonable so far. And, well, certainly this idea of looking at a subgroup is definitely contained within there, right? Because definitely if H is a subgroup, the inclusion map of H into G is a homomorphism. So that takes care of this already very reasonable case. And in fact, this allows us to be a little bit more general, right? Because normally we don't care about a group up to, or we don't care about the particular model we're taking of a group. We really care about it up to isomorphism, right? So I don't care so much, oh, if G has a subgroup, like literally set theoretically it's this subgroup. I care, oh, does G have a subgroup that is isomorphic to some given group, right? So the way then, if we chose, say there was some other group H prime, right, some other model for the group H, and this was isomorphic, I could compose these two things, and this would be the same as just saying that there is an injective homomorphism between H prime and G, right? So that's an equivalent way of discussing subgroups. Now, what is the dual concept, right? Of course, for thinking algebra, maybe vaguely aware of some category theory stuff, we might wonder, well, what should be the dual concept to thinking about an injective group homomorphism? Hopefully you're thinking right now that that should be a surjective group homomorphism, right? So the other thing we might want to consider is what if we have a surjective group homomorphism, right? So certainly Q, just like H is some approximation to the group G, Q is also an approximation, right? We have some surjection. You're maybe forgetting some information from G, right? Because multiple elements may go to the same thing, but this also to some extent captures the structure of G. It sort of cuts it down a little bit. Now, what's interesting in this perspective, hopefully you have some familiarity with the first isomorphism theorem of group theories. Probably one of the most important theorems. It's really, really useful for proving two groups are isomorphic. Surprise, surprise. So what does the first isomorphism theorem tell us? Well, it says that if we have a surjective map, then the group G quotiented out by the kernel of this surjective map is isomorphic to Q. And in fact, it gives us more information. It tells us specifically how we can define a particular isomorphism built in terms of pi. Moreover, here's another useful equivalence. Well, the fact that we can take this quotient, for that to even make sense, we know that the kernel of pi has to be a very particular thing, right? So the kernel of pi has to be a normal subgroup of G. And in fact, here's what's true for every, so this is true because for any group homomorphism, the kernel, for all f from G to H, the kernel of f is a normal subgroup of G. This is true. And not only that, but for every normal subgroup of G, there exists some map, definitely more than one, some other group H and some map, such that n is equal to the kernel of phi. In particular, this will be the case if you just look at the map from G to its quotient, where you just send G, an element G to its coset, right? So kernels and normal subgroups are basically the same thing. Okay, and so here's a neat thing that we learn about this, right? Because you say this problem that we had before when we were trying to study just an ordinary subgroup, and the question was, okay, I can study that subgroup, but what about the elements that are outside of it? In the case of Q, the thing is, you don't have so much of this problem, right? Because yes, you might lose some information. Two elements might get collapsed to a single point in Q, but somehow they all are determining something in Q. So the information's lossy, but at least everything determines an element of Q. But what's even better is if you're worried about that lossy information, well, what are the things that are lost in that information? It's the normal subgroup that you quotient out by, right? So if you have a quotient, what you can do then is you can study the normal subgroup, which is the kernel of said quotient. Oops, sorry, there should be a G. And now the beautiful thing about this is that every element of G either belongs to the normal subgroup, and now you can study the normal subgroup and its behavior and the extent to which that captures all the information about G, or for any element now that lies outside of the normal subgroup, that will now determine a non-trivial element in the quotient group, G mod the normal subgroup. So this is fantastic because so we realize that actually normal subgroups are the things that we really want to be studying when it comes to group theory. So what should it mean, with all of this in mind, what should it mean that a group G is built out of two other groups? Well, here's what we could say. So G is built out of N and Q if there is a surjective homomorphism from G to Q, call it pi, such that, and remember, again, we don't want to commit to N having to take on the particular model of being a literal set-wise subgroup of G. And so if I scroll back up here for a moment, where did I put it? Right where we had this H prime mapping into G, right? An injective homomorphism into G. So what it should be is that G is built out of N and Q if there's a surjective homomorphism of G onto Q such that there's an isomorphism. There is an isomorphism from N, this group, to the kernel of pi, right? So that's exactly what we want. Now, there's a way we can be a little bit more succinct about these things and package them all together. So how do we do that? This is where the notion of exact sequences come into play. So we can tie these two things together, right? So what I really want is I have my map G, I have pi and Q, and well, perhaps I should review for you first what the notion of an exact sequence is. So let's look at the definition first. So a sequence of groups. A sequence of groups. I don't know why I made the G uppercase. Let's say F, so ... G1, GI, FI, GI plus 1, FI plus 1, GI plus 2, and so on and so forth. So potentially infinite, but there are many cases that we will look at in which we only consider finitely many terms, but is said to be a chain complex, or just a complex, if for all I, the composition of Fi plus 1 with Fi is the zero morphism. It is said to be, so in other words, equivalently, this is the same as saying that the image of Fi is contained in the kernel of Fi plus 1. The sequence is said to be exact at position I if the image is equal to the entire kernel. So it's always going to be a subset, subgroup. But if it's totally equal, then it's exact. So as an example, imagine we had a sequence that was 3 terms long. So here's our map pi. And there's only one map from any group to the trivial group. So sometimes we write 0 for the trivial group, the group with one element. And I will put a 0 here. So what would it mean? So since there's no other terms here and there's no other terms here, it doesn't make so much sense. I mean, we could imagine that they just keep going as zeros forever, but we'll just ignore those other terms and we'll just look at the middle of the sequence. What would it mean for this sequence to be exact at the position where Q is? What would that mean? Well, that should mean that the image of the map pi is equal to the kernel of the next map in the sequence, which is the 0 map. But the 0 map is the group homomorphism that takes every element of Q and sends it to the identity. So that means that by definition, everything is in the kernel of Q. So what does this say? This says that the image of the map pi is equal to Q. What? This is just another way of saying that the map is surjective, right? So that's what exactness of this sequence means at Q. Okay, and again, being dually minded, right? So here's quotients. Let's go back and think about what is the corresponding notion if I had now instead a 0 on the left, and I had a G, let's say an N here, and a map, let's say I. And again, this is very suggestive notation. What would it mean? Well, okay, let's also think the trivial group has only a unique map out of it as well, right? The trivial group has one element, the identity. We know that a homomorphism has to send the identity to the identity. We have no other choice. This is just, again, the 0 map. It sends everything, which is just one thing, to the identity. What would it mean for the sequence to be exact at n? Well, it would mean that the image of the 0 map is equal to the kernel of I. But the image of the 0 map, as we just said, this is just the identity element of n. But if you're familiar enough with group theory that you've followed the video to this point, then you should know that a map having, if the kernel of a map only contains the identity element, this is exactly equivalent to that map being injective, right? So exactness of this sequence is equivalent to being injective. Okay, fantastic. So injectivity, surjectivity, these are both codified by the concept of a short exact or exactness of a particular sequence. We can combine these two examples together, right? So let's say I'm going to write G and H now, but let's say I had some homomorphism here. Again, I put zeros on either end. So now I have a sequence, it's a little bit longer, right? A sequence that has 4 terms. And what if I demand that simultaneously the sequence is exact at this position and exact at this position? Well, that means precisely that F is an isomorphism, right? As we just saw, exactness here means that it is injective, and exactness here means that it is surjective. Therefore, it's a bijective homomorphism. It's an isomorphism of groups. So finally, we will come back to this example. We will stitch these things together. And how are we going to stitch these things together? So perhaps I will scroll up just to remind ourselves where we came from, right? So we came to this decision, this idea that G should be considered to be built out of groups N and Q. If there is a surjective homomorphism from G onto Q, and an isomorphism from N into the kernel of pi. So I claim that this is equivalent to saying that there is a sequence of maps, so necessarily the zero map here, N, and we'll call this map F, into G, and G, maybe I'll call this map, H. Perhaps I should call it I and pi, just to be somewhat consistent with the previous notation. So I and pi into Q. And now I claim that our previous definition is equivalent to saying that this sequence is exact in all three positions, right? So again, as we've already investigated, exactness at n tells us precisely that I is an injective homomorphism, right? And this was part of the condition that we wanted. We wanted to say that n was definitely isomorphic to a subgroup of G. That was definitely part of what we wanted, right? Exactness at Q tells us that Q is surjected on by G, right? That was also part of it, right? And then the one other important part is that we wanted not only N to be isomorphic to a subgroup, but specifically we wanted there to be an isomorphism from N to the kernel of pi, right? And that's where the final piece comes in. If we ask ourselves, well, what does exactness at the middle term in the sequence mean? Again, this means that the kernel of pi is equal to the image of I, right? But because we know from exactness here, I is an injective homomorphism, we know, therefore, that the map I gives us an isomorphism to the image of I, which is exactly equal to the kernel of pi. And this is the condition that we wanted, right? So exact sequences do so many things for us. Number one, we've already seen that it's as a very tiny special case where it gives us a way to talk about injections, surjections, bijections, all in this uniform language. And now it also gives us a way to discuss how G can be built out of two groups, right? So our general definition to say that G is built out of two groups is to say that there is a short exact sequence between them. So short, meaning even though it's not as short as the other ones, that there are three terms appended by zeros. And exact, meaning that it is exact at all three of these positions. So I think actually semi-direct products we're going to leave to the second part. This is going to be a mini-series because this video's gone on for a little bit. No one has an attention span anymore, least of all me. But I will leave you with a challenge to just verify, right? This whole thing began when we were considering what are the ways to combine two groups. And we said, well, one way is definitely to form the ordinary direct product. So certainly the Cartesian product of two groups is built out of the two groups that you're taking the product. So it should be the case that we can describe this in terms of short exact sequences. And so I claim that the following does give us such a short exact sequence. So we have G into G cross H and into H. Necessarily, these are the zero maps. And what are the maps? So this first map here will be G goes to G, comma, and the identity of H. So that will be this first map here. You can give it a name. If you like, you could call that I. We'd call this one pi. What is the second map going to do? It's going to take a pair GH and just send it to H. And so I will leave it to you as homework to verify that all of these things are group homomorphisms. and that this does define an exact sequence. Okay, so in the next episode, we will start to turn our attention towards the definition of a semi-direct product. I will see you then.